Okay, welcome back. We are going to begin right now the first lesson of our final unit of the year. Seniors are gone, and we're going to learn about models of computation. This is something that you might know about a little bit before, especially if you've done some kind of theoretical computer science, whether that's ACSL or maybe you did some stuff with the computer team. Anyway, if not, I will explain it. Hopefully this will be kind of intuitive, and this is this is the theoretical computer science component of this class, I suppose. Okay, what's going on? There are these things. They are called finite state machines. But some people don't call them that. Some people call them finite automatons. Or the singular is finite automaton, and the plural is finite automata. So just, whatever that is, Latin or something. So you will see them abbreviated FSM or FA for finite automaton, or even FSA, I think is actually maybe the most common, I don't know, finite state automaton. What is it? It's a machine, okay, but not literally a machine. It's a theoretical machine for processing strings of characters, and what this machine does is it accepts some strings and rejects other strings according to certain criteria. Okay, I'll give the formal definition in a second, but first let's just see an example and kind of work through this example to get a feel for this. I think it's pretty intuitive. What you have, actually no. Before we check the example, let's just kind of talk out the general gist. Okay, so there's just like a lot of vocab, which I'll give informally and then I'll give formally in a minute. So first of all, you have these things called states. What is a state? It's kind of like a you're all used to programming. So when you're programming something and you have written an algorithm, and an algorithm steps through certain stages kind of in a computation, you can think of a state as being one of those stages in that computation. It's a point you are in the algorithm, but not in the general algorithm. It's a point you are in the execution of the algorithm on a particular input. Something like that, maybe. Maybe that's not even right, what I just said. You have some states, you'll see in a second. There's always a start state. So the start state is just where you start. And this little arrow here, sort of coming from nowhere, is the indication that this Q1 state is the start state. What else? We have some string. And the string, in this case, the string is going to be composed of zeros and ones, but you can make a machine to recognize any kinds of strings. And what we're going to do is we're going to read this string one character at a time. And the thing about these finite state machines is that they just operate with sort of a cursor that can only read the specific character that we're on. And once we read that character, it's sort of gone, right? So we process in a certain number of stages every single one of the characters of that string. And in fact, if the string is 20 characters long, then there are going to be 20 things that this machine does. All these strings are finite, so eventually the computation will stop. Also, there are a finite number of states. That's why it's called a finite state machine. And then we have these rules. What are the rules? The rules are for transitioning from one state to the next. So you have these certain finite number of states, and based on what character you've just read and what state you're in, you sort of transition, is the word people use, to new states. And finally, eventually, after processing every single character from the string, we will try to determine whether the machine either will accept that string or reject it. This is, I don't know if that was helpful at all. Let's look at the example. Maybe we should have gone straight to that. Here we have a machine with three states. State Q1, Q2, and Q3. Q1 has been designated as the start state. And like I said, because there's a little arrow here or whatever. Okay, and what do you do in Q1? Well, you just are chilling here in Q1. And now comes your string, or rather you begin to process the string. And this particular machine is designed to accept strings composed of characters which are either 0 or 1. And so what you will see here is a rule for what to do in state Q1 when you read a 0, and what to do in state Q1 when you read a 1. And, okay, here it is. This arrow is a sort of a, it's basically telling you, dude, if you read a 0, the label on the arrow is an indication that this arrow is describing what to do when a 0 is read. Go back to Q1. So if you're in Q1 and you read a 0, just go back to it. And if you're in Q1 and you read a 1, then go to state Q2. Okay, what happens in state Q2? Well, once again, I need to give directions for what to do when I read a 0 or when I read a 1. If you read a 0, go to state Q3. If you read a 1, then stay in state Q2. If you're in Q3, whether you read a 0 or a 1, you should go back to state Q2. And you basically just keep following all of these rules, jumping around from state to state, working your way through the string one character at a time. And whenever you read the last character in the string and follow the last direction, then you land in a certain state. And then we have the designated, and that is the meaning of this sort of double concentric circle here. We have designated Q2 as the so-called accept state. And what that means is that if the string terminates in state Q2, then you accept the string. And if the string instead terminates in Q1 or Q3, you don't accept. Okay, so let's just do some examples. So, or this is an example of a machine. Let's do an example, sort of run of the machine, or computation, people say. Okay, so if you take 1, 1, 0, 1, that is certainly a finite string composed of zeros and ones. So let's see what this machine does when the string 1, 1, 0, 1 gets processed. Okay, so we just follow along. I think it's pretty simple, right? We start in state Q1. The first character is a 1. So we go from Q1 to Q2. Okay, now we're in state Q2. And we've already read this first character. So now read the second character, which is also a 1. So we also stay in Q2. So we're still here in Q2. Then we read a 0, and we follow this rule which says go to Q3. Now we're in Q3. And finally we read a 1, and this sends us back to Q2. Oh, this 0, 1 is just a way of saying, dude, I don't feel like drawing 2 arrows. Okay, I think that's pretty clear. Anyway, we end in state Q2, right? It was 1, 1, 0, 1, so 1, 1, 0, 1. And since that's it, and there's no more string left to read, then we land in state Q2, and therefore, since Q2 is an accept state, this machine accepts this string, and that's the language that we use. Okay, question, and I think this is hard personally. What strings does this machine M1 accept? Okay, so now I'm asking a kind of harder question. I'm asking you, at the moment we have no sort of systematic algorithm for this or whatever. I'm asking you to use your thinking powers to look at this machine, scrutinize it, use a lot of examples and playing around, and try to figure out some way of describing all the strings which this machine accepts. So all the strings which terminate in Q2. Okay, well, if you do this, I don't know where to sort of begin. Well, okay, I don't know. One thing, what's maybe the simplest string that this machine accepts? Well, it will accept just 1. Because if I'm in Q1, I read a 1, I land in Q2, that's it. Okay, but also it could accept 0, 1. Because if I'm in state Q1, I read a 0, and then I read a 1, then that's also going to work. In fact, any number of zeros prior to a 1, that string also is accepted by the machine. But then, of course, there are other ways to be accepted. You could have a bunch of zeros, and then a 1, and then any number of 1s after that. So, yeah. So I don't know, like 2 zeros and a 1, but then like maybe just like a bunch more 1s or something. Also is a string which is accepted. And then notice that we could also visit state Q3, which we haven't really done yet. So one thing that could happen is we could have a 1, and maybe like another one, maybe like another one, and then perhaps a 0. But if I'm going to get back to Q2, there needs to be now like another thing after that, basically. And maybe that's just like a 1. So I think this is easy, right? 1, 1, 1, 0, 1, and now I'm back at Q2. But also maybe more of those. So maybe 1, 1, 1, 0, 1, 0, 1, 0, 1, etc. That will also work, right? 0, 1, 0, 1, 0, 1, 0, 1. Okay, could I have, so that's possible, but I could also, by the way, I could also have some zeros. So I could have, I don't know, 0, 1, 1, and then maybe a 0 followed by another 0. But I could also have, like, I don't know, 0, 1, 1, followed by another 0 and another 0 and another 0. So, okay, so maybe like it ends in 4 zeros or something. And, okay, and this pattern just sort of continues. Okay, so this is, I think, tricky. This particular machine is sort of not obvious, I think. And I think in general it can be quite hard, especially if there are more states to figure out what a machine does. And we're going to pursue sort of a more systematic approach to this. But for now, I think the best way to articulate this is that the set of strings that this machine accepts is all the strings which either, okay, well there are two things I want to say about them. There's got to be at least a 1, because I start in state Q1, and if the string consists of only zeros, then there's just no way that this machine is going to ever get to Q2. So somehow to get to Q2, I have to have at least 1, 1. So W contains at least 1, 1, and what is the other property that every one of of these strings that we mentioned has? Well, it seems like you can sort of have a bunch of 1s. You can have a 0 and another 1, and you can then stop. But if you have a 0, then you can, let's see, well, basically you can't end in an odd number of zeros, I think is the best way to put it, right? The one kind of string that isn't possible to create is a string that ends in, say, 3 zeros. Because if you want your string to end in 3 zeros, you somehow need to go 0, but then like another 0, and then like another, it just doesn't work. So the solution to this problem is that W contains at least 1, 1, and an even number of zeros after the final 1. After the final 1. Alright, so that's awkward and to write, and we don't have really a language to talk about this yet, but I think this is just correct, that this is the set of strings that this machine will accept. Okay, let's temporarily call this set A. And now let's introduce a little bit of vocab. So we call, I guess I'll just write this down. We call the set of strings A that M1 accepts. That M1 accepts. We have a name for this set. We call it the language of that machine. The language of M1. Sha. So in this case, the language of M1 is A. And we say that M1 recognizes A. This is another kind of piece of vocab here. A machine recognizes a certain language, the language being just a set of strings, when that set is precisely the strings which are accepted by that machine. And so, just to be clear, and people aren't always so careful on this, and maybe not always am I, is that machine M1 accepts, the verb we use is accepts a string, or it might reject it, but a machine M1 recognizes a language. Recognizes a language. Okay, so cha. All right, good, well, good. Okay, this has sort of just been one long example, or short example, I guess. Long conversation. Let's continue on, and I guess the next thing to do is to just do this all formally. So okay, let's go. And I should say that I think Gossett is pretty good in this chapter, but not as good as sort of the kind of industry standard. And so my point of reference is this book, which I think is really great. It's called Introduction to the Theory of Computation by Michael Sipser. This is a very old book. And it is, I think, designed for computer science undergrads, and it was actually one of my absolute most favorite classes that I took in college, which was meant for sort of senior computer science majors. But I was a math major, and I was very interested, and I took it, and it was basically like something like called theoretical computer science or something like that. And this book is just brilliant. And so well done, and I read every single word of it, and it walks you through all these things. In fact, material is just the very first page of the first chapter, and it walks you through. This is a sort of meant to be a semester-long course, and so this is just a little bit better. So I'm going to use this book kind of a lot for these last 3 weeks as kind of a reference. And Gossett doesn't mess up a couple things that this book gets right, so that's very helpful. Okay. Oh, and we're going to go beyond what Gossett does in a couple of key respects, and that's because I know all about all this stuff, or I used to. I did all my homework that semester, so I learned it quite well. What is a finite automaton exactly? Okay, well, I don't know why we have A here. Well, okay. So what is a finite automaton? It is technically 5 things. It is a 5-tuple. And so if you're all into, reducing every single mathematical object down to the kind of language of set theory, I like to do that, then this is a 5-tuple. It consists of S, sigma, T, S naught, and F. Okay. And so if you have completely specified these 5 objects, these 5 mathematical objects, then you have completely specified your finite automaton. Okay, what is S? Well, this is just a set of states. Okay, so it's a finite state machine, so it's a finite number of states, so you simply tell me what those states are, and you represent it as a set. Okay, next. There is sigma is the alphabet. This is, okay, what is the alphabet? It's simply the alphabet from which characters are drawn to make the strings. So I'll try to say this sentence one more time. Every string that this machine is going to deal with is a string composed of a finite number of characters in sequence, and those characters themselves have to be drawn from some larger finite set of characters that the machine is going to talk about, and that's sigma. So you design a machine to accept a certain kind of input, and from our previous example, well, I'll tell you in a second. So you can think of it as the possible inputs or something like that. Okay, then there's T. This is the transition function. Transition function. And the transition function basically describes what this machine A should do in every state. And it's going to depend on what state we're in, and also what character we just read. And so, formally speaking, t is a function. And it's a function which takes you from, okay, here comes some, fancy mathematical language. It takes you from s times, this is like the Cartesian product of s and sigma to s. In other words, what t does is it takes an ordered pair and it outputs, it takes an ordered pair of a state and a character from an element from the alphabet, in other words, a character, and gives you back a state. In other words, it just tells you, based on what state you're in and what character you just read, what state to go to next. That's the idea. Okay, this thing S0, this is just the start state, is the start state. So you must tell me what state that we are going to start our computation in, and it must be true that this start state is one of the states. And finally, we have F. F is the set of accept states. Okay, and so the set of accept states are, so this is just F is some subset of S. And if the string finishes in some one of the states which is in F, then A accepts W. Okay, I don't think I need to write that down. I now realize that I erased my example and I am so sad. Let me just quickly redraw it. Sorry. Here was Q1. Here is Q2, which was an accept state. And here was Q3. And I think I stayed here with 0. I go here with 1. Here I do 1s. And here I do 0s. And here is 0, 1. That's just the machine, right? Yeah. Okay, good. So this was a machine that we talked about for 5 minutes. Let's make sure we understand this technical definition. Perhaps I should write this. So sort of just like note. Note if string W finishes, although that is itself vague, in S, and S is one of the states in the set of accept states, then machine A will accept string W. That's the idea there. I don't know if that loose explanation helps anyone, but okay. Okay, so just to make sure we get it, looking up at our example that we've already sort of talked to death, what would a full technical specification of this machine above, what would that entail? Well, of course, S, you would tell me, is a set of states. So Q1, Q2, Q3. And then you have to tell me what sigma is. And and as I already said, in this case, sigma is 0, 1. So notice that this isn't sort of important because once you specify the alphabet, then you have committed to accepting strings that can consist of 0s and 1s and 0s and 1s only. Therefore, you will note up here in this machine that I told you what to do at every single state for each of the inputs 0 and 1. But I did not tell you what to do for input, say, 2, for example. So that information is not sort of contained in the picture, but okay, here we're sort of being precise that this machine is only designed to deal with inputs which are 0 and 1. 0s and 1s, composed of 0s and 1s. Okay, and that's, I think this is maybe best explained now, that T, what is T is the transition function. So this transition function is now going to tell me what to do for every single state that I am in, and every single one of my characters. And I think the convenient thing to do is to organize this into some kind of table. And okay, now we're getting into some sort of weird representation thing where it's like, humans like the picture. But maybe computers, if you're going to code this or something, would prefer this information to be contained in some kind of a matrix. And people who don't care about anything will just tell it like it is, which is that it's a function. So it's a function which takes an ordered pair and outputs some state. So what is this function? It's sort of a set of ordered triples, or an ordered pair of an ordered pair number, or however we look at it. Okay, and anyway, this diagram says, dude, if you're in state Q1 and you read a 0, then you should go back to Q1. And if you're in state Q1 and you read a 1, you should go to Q2. If you're in Q2 and you read a 0, go to Q3. If you're in Q2 and you read a 1, go back to Q2. If you're in Q3 and you read a 0, go to Q2. And if you're in Q3 and you read a 1, go to Q2 as well. So this, I think, table perfectly captures what is captured in that diagram with the arrows. But anyway, it's just a function. Finally, we have, I have to tell you what the start state is. So okay, we've indicated this with this little notation, but in the full specification you would say that, you know, Q1 is the start state. Finally, what is the set of accept states? It's just the set Q2. Okay, because there's only one accept state. All right, so this I think is the amount of detail we want to go into, you know, at most. But we need to have this concept of finite state machines to be precise enough that we can sort of prove theorems about them and stuff like that. But I don't really need this extreme level of detail. Note that almost everyone just draws it with these pictures because I think human beings find these sort of easier to cognitively process. So the start state, whether something is an accept state, sort of what to do, the transition function, that's what the arrows are. But just like in the graph theory unit, you know, the finite state machine itself is not the picture. The finite state machine is the explicit listing or specification of the set of states, the alphabet, the transition function, where the start state is and what the accept state is. Okay, good. Now I think that's it. This is just way more thorough and organized than the normal lesson I give on this topic, which is I just kind of wing it. In fact, always, which is why I had no notes whatsoever for this subject. But anyway, while I have you here, let us do a bunch of examples. And maybe this will only take like 5 or 10 more minutes. Yeah. Woo! Okay. So, and these are all just taken, you know, directly from this book. So I'm not even I didn't really even do any real effort here in preparing this lesson. Okay, here's a new machine, and we're just going to draw it and then talk it out. So it starts in state Q1, and then there's just only one other state. It's this state Q2. And okay, I will do this the casual way that people do, which is they just do this. And okay, it's clear that the start state is Q1. It's clear that Q2 is an accept state. It's clear that the only states are Q1 and Q2 because, dude, that's the only pictures I drew. It's clear that the alphabet is sigma because I've only given rules for what to do with zeros and ones. So okay, great. Here's everything you need to know basically contained in this diagram. All right, what does this machine do? Well, I don't know. If we were doing this live, I would give you a minute to think about it, and I think this one is by contrast, not that hard. Yeah. Well, we start in Q1, we read a 0, so somehow I read a bunch of zeros, and if I'm reading zeros, I kind of do nothing. What you need to do is you need to begin to sort of psychologically associate each of the states with some kind of meaning. So my meaning of Q1 is something like twiddling my thumbs, reading a bunch of zeros. Zeros are somehow irrelevant to me or something. But then I read a 1. And if I read a 1, I suddenly get very happy. In fact, I'm so happy that I'm about ready to accept this string as is right now. And if more 1s come, I stay happy. But as soon as a 0 comes, I become unhappy again. So, okay, I think I basically just got this, right? This machine wants to end in a 1. And if you got a bunch of zeros, it's unhappy. But if you got a 1, it's happy. And it stays happy as long as you keep feeding 1s. If you feed a 0, it becomes unhappy again. So if this machine ends, if a string ends in 1, this machine will accept it. And if the string ends in 0, this machine will not accept it. And so that's it. The language, we say, Gossett I don't think uses this notation, but anyway, the language of this machine, remember, this machine accepts or rejects certain strings. The language is the set of all the strings that the machine accepts, and the language of this machine is the set of all strings such that W ends in a 1. And we say that M2 recognizes this language. Okay, that's pretty easy. Let's do another one. Let's take the same. Let's take the same basic picture, but now let's make this an accept state and this one not. But otherwise, I'm not going to change the number of states, the alphabet, or any of the transitions. We're just going to flip it. Okay, well now I begin extremely happy, and then yeah, when I read a 1, I become unhappy, and then I stay being unhappy reading 1s, and then when I read a 0, I become happy again. So this is basically the machine which ends in a 0, except there's one kind of twist, right? The one twist is that, in this case, the start state of the machine is also one of the accept states. And if the start state is also one of the accept states, then that means that this machine will accept a string which is 0 characters long. And the null string is actually really important, and okay, most authors will use sort of epsilons for that, but Gossett uses lambda, so I'll use lambda too. Also, my lambdas are really bad. So the language of M3 is any string that ends in 0, but also this machine accepts the empty string. So I guess I just write that, right? So it's all the strings W such that W ends in a 0, or W is in fact just the empty string. And we have this sort of special character, lambda, which we use to refer to a string, the null string, the empty string, the string of length 0, consisting of no characters. Okay, and it's a legit string, and it's in fact accepted by this machine. It's in that language. Okay, this can be combined. This concept can be combined together in a kind of a sort of a cute way, which is if I have S, then I can. Okay, this is A. This is B. And here is, okay, so I'm basically just what I'm now gonna do is I'm gonna sort of stick these two machines together, so to speak, in a certain kind of way. And, okay, this is B, this is A, I want it to go this way. Oh, okay, so